Hello everyone and welcome back. This is Ahmed for Eduonix and this is the third section of our course Beginning DevOps. And in this section we are going to study containerization with Docker. So first of all, of course, the natural question to pop up is, what is Docker? Docker is a way of running multiple software applications on the same machine, each of which is run in an isolated environment that is called container. And please take a very good notice of this definition. It is running multiple software applications rather than running multiple virtual machines on the same machine. We will come to that later, but just take a notice of that important distinction. Docker eliminates the annoying problem of works on my machine. Software is packaged in the container and hence can be run on any machine that has the Docker engine installed. Currently, Docker is supported on Linux, of course. All flavors support Docker, or all major flavors support Docker. It is also supported on the Mac OS, and recently it has been adopted in Windows, but you will have to have a Windows 10. You will have to have the latest version of Windows at the time of this recording, which is Windows 10, in order to be able to run Docker. Previous versions of Windows did not support Docker. So what is a container? A container is a closed environment for the software. Think of it as a chroot. If you've worked with Linux before and you have an idea about chroot, chroot is just a way of jailing an application or a process so that it cannot interact with the parent operating system. If you don't have an idea about chrooting, that's okay. We're just giving an example here. So a container bundles all the files and libraries that the application needs to function correctly. Multiple containers can be deployed on the same machine and share the same resources. So the important question arises again now. But isn't that what virtual machines and Vagrant do? Well, not exactly. Virtualization is the process of abstracting the operating system hardware, the CPU, the memory, the network, and so on, so that complete machines can be run simultaneously on the same host. Containers, on the other hand, use the same physical hardware of the host machine to run just the application in an isolated environment. We will have this distinction more clearly demonstrated when we start creating and deploying containers on our example system. You are going to understand clearly the difference between a container and a virtual machine. So, containers by definition use less resources than virtual machines, and that is one important advantage of using Docker or containers to virtual machines. However, they have the drawback of using Linux kernels only. You cannot containerize a Windows or a Mac application. So in order to use Docker, the application that you are going to deploy must be on a Linux kernel, must have been developed or must work on Linux kernels and Linux kernels only. You cannot package an application that needs a Windows environment or a Mac environment in a Docker container. So how does it work? You learned that Vagrant uses boxes to distribute virtual machines. A box can be used to spawn multiple machines. Docker works in the same manner. It uses images to spawn containers. An image is like a template to the container, just like the box. If you have watched the previous section in this class where we discussed Vagrant, Vagrant uses boxes, and boxes are a template from which you can create multiple Vagrant machines. Docker works in the same manner, but it uses images instead of boxes to spawn containers. And of course, Docker is not like Vagrant technically. I'm just listing the points of similarity just in the manner or in the way both of them works, but technically they are totally different. Docker is a containerization platform while Vagrant is a virtualization platform. So images are templates to spawn containers, and multiple containers can be created using a single image, just like multiple Vagrant machines can be created using a single box. Images are indexed and saved in an online repository that is managed by Docker. It can be found on this URL, hub.docker.com/explore. However, you can also create and maintain your own images. There is nothing that prevents you from creating an image, a Docker image, placing it on some website that you own or that somebody else owns, and making this image publicly available for you and your colleagues to work with, or in making it publicly available for anyone who needs to download and use it. However, this URL, if we click on it, will bring this repository of different containers. As you can see here, there are a lot of containers that are available for you. Multiple pages just have a quick look, you can see that they have most of the needed software. We have here a container that runs Ruby, a container that runs Python, PHP, MariaDB, even Jenkins, and let's have a look here. MySQL, Ubuntu. This is just the OS. No applications are running. This is just the OS. I have here MySQL, MongoDB, and so on. So I guess by now you have a clearer idea of what a container does. It holds an application, just as you can see here. It either holds an empty OS, where you can further deploy an application, or it contains a ready-made application, like as you can see here, Redis, Eduonix, and so on. So to understand the power of Docker, consider the following example. You have a web application running on Ubuntu 15. You need to upgrade your OS to the latest Ubuntu 17. But then, the software will not run as it depends on libraries that are only available in Ubuntu 15. Using a Docker image to run this software, you can upgrade Ubuntu to the latest version and ensure that the application will continue to run in complete isolation of the OS current libraries. So what a container is going to do in such a scenario is that it is going to abstract the libraries and the files and any dependent packages or applications on the OS that the application needs to run. It is going to abstract those entities in an isolated environment, and that environment is going to run regardless of the version of the OS you're running. So you can run Ubuntu 17 and have an application that should only run on Ubuntu 15 because of some files and some libraries that are only supported in Ubuntu 15, like for example the famous glibc library, which is tightly connected or which is tightly coupled with the version of the kernel or the version of the OS. If you upgraded the operating system, if you upgrade the glibc, you will also upgrade the kernel and possibly the version of the operating system. So if you have a software that only runs on a specific version of glibc or a specific version of the operating system, you can use a container for that, and you can now upgrade the OS to the level that you need, even to the latest version, and you're going to be sure that the software will continue to run and function properly. And that brings us to the end of this lecture. In the coming lecture, we are going to actually install Docker and build our first container, so see you next. Alright, welcome back. This is Ahmed again for Eduonix, and this is Beginning DevOps, Section 3, Containerization using Docker. In this lecture, we are going to start by installing Docker and building our first container or having our first example. Docker can be installed as of the time of this recording on Windows, Linux, and Mac OS. But it can only run applications designed to work on a Linux kernel, as we mentioned in the previous lecture. Currently, Docker supports two flavors, the Community Edition and the Enterprise Edition. The Community Edition is free of charge. You can use it without paying any charge for Docker, but you will not receive the official support. If you have a problem or if you need assistance with some of the actions or some of the features of Docker, you will have to resort to the internet and the community support. And actually, Docker has a very vibrant community, and lots of people are willing to help other people out on the forums and on the different websites that deal with Docker. However, if you are working in an enterprise or if you are using Docker for serious applications, you will need to install the Enterprise Edition. The Enterprise Edition is a paid version, but it gives you enterprise level support. It gives you official support from the Docker team. The following page lists the different versions you can use and the download links. So let's have a look at this page. Okay, and as you can see here, Docker is supported on CentOS, Debian, Fedora, Microsoft Windows Server 2016, Oracle Linux, Red Hat Enterprise Linux, SUSE, and Ubuntu. But notice here that the Community Edition is supported on only a fraction of the whole stack. So it's supported on CentOS, which is in itself a community-based operating system. Debian and Fedora are the same, but the operating systems that have official support that have paid support, like Microsoft Windows Server 2016, Oracle Linux, Red Hat Enterprise Linux, and SUSE, those can only accept installing Docker Enterprise Edition. The Community Edition is not supported for these operating systems. Docker installation on any operating system is as simple as installing any package, nothing complicated and nothing complex. In our class, we are using an Ubuntu 17 OS for the demonstration. So I have created a virtual machine for Ubuntu, and I'm gonna use it to install Docker Community Edition. So let's get started. So here is the Ubuntu machine that I have created. I'm gonna start it up. Okay, and once inside, let's just close those messages. I need to open a terminal, and once inside, I will install. I'll first use apt-get update, because this will update the repository sources on Ubuntu. Actually, this is essential. Whenever you install Ubuntu for the first time, you'll have to update the software resources. Once done, we can start by installing the prerequisites. The prerequisites for Docker are as follows: apt transport, HTTPS, CA certificates, curl, software properties, common. Okay. And if you have this error, couldn't get a lock on /var/lib/dp/kg/lock, this means that the system is trying to automatically search for new packages, and this is something that is done automatically in Ubuntu. So you'll have to search for the command dpkg. Okay, using sudo and using your normal user, and if it is found, just kill the process that is using it. And once done, you can start installing those prerequisites. Do you wish to continue? Yes. And it's going to download and install the prerequisites for Docker. Now once done, you are going to use curl with this command line options. This is actually mentioned in the presentation, so you don't need to memorize this. We are just going to use curl to download the GPG key that is used by Docker to verify the installation. That is a security measure, so that you are sure that you are installing the correct application or the correct binary. And sudo apt key fingerprint, and give it the fingerprint that is provided to you by Docker. All this can be actually found on the Docker installation page. I just copied the commands of the website. Okay, and okay, the fingerprint is okay. Now we're ready to add the repository, so sudo add apt repository, then this repository. I'm gonna write it quickly. Okay, press enter to add the repository. Now let's do a final apt-get update to update the software repositories with the new repository that has been added. Just gonna take a few seconds to complete. And now you're ready to install Docker by using sudo apt-get install docker-ce for Community Edition. And that is going to download and deploy the application on your operating system. Okay, once done, let's clear the screen. And whenever you want to use Docker, you will need to use sudo. So in order to verify the installation, we are going to run sudo docker run hello world. This is just a sample container provided by Docker. Of course, the image can be found locally, so it's going to be downloaded quickly from the repository. Okay, and it has downloaded the image. And as you can see here, this message shows that your installation appears to be working correctly. Now you are ready to start working with Docker. That brings us to the end of this lecture. In the coming lecture, we are going to start with exploring the Docker file, which slightly does the same function as the Vagrant file when we were using Vagrant. So until then, see you next. Okay, hello everyone, welcome back. This is Ahmed again for Eduonix, and this is Beginning DevOps, Section 3, Containerization using Docker. In this lecture, we are going to start by discussing the Dockerfile. In the previous lectures, we have learned what Docker is, the difference between Docker and other similar platforms like Vagrant, and we have mentioned that Vagrant and Docker are totally different in how they manage their entities. On Docker, containers are managed and they abstract the applications, while in Vagrant, virtual machines are used and they abstract the hardware of the host machine. So in order to use Docker, and actually more technically, in order to build a Docker image, you will need to have a Dockerfile. And that is one important difference between Vagrant and Docker, which is that in order to use a Vagrant machine, you will need to have a Vagrant file. You must have a Vagrant file in order to start working with a Vagrant machine, in order to start launching a Vagrant machine, even if you won't be doing anything to that machine. Even if you're not going to install or change anything on the machine, just to launch the machine, you will need to have a Vagrant file. In Docker, however, you can run and use a container or download an image from the Docker repository or from anywhere else without having or without needing to have a Docker file. But Docker file is needed when you want to build an image. And in order to understand that, we will have to understand how Docker works. Docker works, as we have just mentioned, by abstracting the application to a container, to an isolated environment. But how is this environment built? This environment is built incrementally. This means that I can start with an empty OS image for, say, for example, Ubuntu, and then I can have a web server installed on that OS or on that image that contains the OS. Then I can build a new image that contains Ubuntu as the operating system plus the web server or plus Apache, and create a new image out of this, and I can call it, for example, Apache or HTTPD. And actually there is an official image that is provided by Docker that is called HTTPD. We're going to look at it in a moment. And this image actually is what we have just mentioned. It uses an abstract image or a base image that contains a Debian version of Linux, something just like Ubuntu, something that is very similar to Ubuntu, and it installs the HTTPD package or the Apache package, and it does all the configurations that are needed for the web server to run correctly. It sets the environment variables, creates the users, the groups, the files, sets the appropriate permissions, and so on. So the end result is that the user is having an image that has the web server bundled with the Ubuntu or the Debian operating system. The user can just use this image and start working with the web server that is up and running. The user does not need to do anything more than download the image and create a container out of it. So if you want to have an example of the Docker file, let's have a look at the official Docker file that was used to create that HTTPD package. It is hosted on GitHub, and if you want to have a look at the official package here in Docker Hub, let's search for HTTPD. Okay, and as you can see here, the first result here is HTTPD. And you're gonna see here some important notes about how to use the HTTPD in your own projects. And as you can see here, the page is suggesting that you can build a new image out of this HTTPD package. You can build upon that package by using a Docker file of your own. So let's have a look here at this instruction. This Docker file contains, as you can see, from HTTPD colon 2.4, which is the version of the image, copy public-html. This line is copying your own HTML files, your own files that you need to be served by the web server, and it is copying it to the path of the web server on the image. So this image contains a web server. This web server uses this path to serve web files or to serve HTML files. So you can build a new image that is based on the HTTPD image that you've just downloaded or just pulled, and you can build upon it by adding your own public HTML files. And then the end result, after you issue that command docker build-t, and for example you can choose a new name for your image like my-apache2, and referring to the and pointing to the current directory which contains the Docker file and also the HTML files that you have, you can have an image that not only has the web server installed, but also it will use your files. It will just have the application ready to run. You can just launch this image or launch this container and just go to the browser and navigate to the IP address of the container. We're going to discuss networking in Docker later in this section. You will navigate to the web URL of your container, and you're going to see that your application is up and running. This application might be anything. It might be a WordPress application, for example. It might be a static website. It can be anything. The most important thing is that it has been isolated in its specific container, and it only needs this command docker run to run your application without having to install anything on the host machine, without having to install any web server, without having to even have your files on the host. The files, the web server, the OS, libraries and file systems, everything is bundled inside the image, and this image contains your web application or your website. So let's have a look at the Docker file that has been used to create the HTTPD package or the HTTPD image that we have just mentioned here, or that we have just viewed. Have a look here. From Debian, Jesse-backports. This is the name of the image on which the HTTPD image has been created. The creator of this image used Debian, Jesse-backports, which is the name of the image, to build upon it. And the user, and he or she used some environment variables, like the path from which the web files are going to be served, the path. Then he used the run command, mkdir-p, and he created the web directory if it does not exist. He created the directory, and he also changed the ownership of this directory to be owned by www-data, which is the user that is used to run the Apache web server. Then, as you can see here, he's using other environment variables, and he's running some commands here just to configure the Apache web server. Then he is using the apt-get update followed by apt-get install. As you can see here, all this gets run as soon as you build the image. So if you took that Docker file, add it to your machine, and use docker build to build this file, it's going to execute all those commands in sequence. So here it's going to install the prerequisites for Apache, or for building Apache, because this is going to build Apache from source. And have a look here. He is actually building the package. He is using the build tools or the compiling tools to compile the HTTPD package. Make and make install. If you have built software before, you might be familiar with all these lines. It's not mandatory to understand what this Docker file is doing. Just understand that the Docker file will execute all those commands when it builds the new image. Once the image has been built, this command is going to run once the container is launched. CMD for command httpd-foreground. This is the command that is going to run when the container is launched, and it is going to expose port 80, which is of course the web server default port. And congratulations, you have a web server up and running, ready to accept your files. So I hope by now you understand what a Docker file is, what a Docker image is, and how a Docker image is created. In the next lecture, we are going to see how to launch a Docker container and how to interact with that Docker container with Docker commands and subcommands. So until then, stay tuned. Hello everyone, this is Ahmed again for Eduonix, and this is Beginning DevOps, Section 3, Containerization with Docker. In this lecture, we are going to start by reviewing the basic Docker commands, how to deal with Docker containers, how to launch them, how to stop them, how to start them, how to delete them, and so on. All commands that deal with Docker containers and images start with the word or the command Docker. So Docker, and then it will be followed by a subcommand, and that subcommand may or may not have some switches that will alter its behavior according to your needs. So for example, I can issue a command like docker images. Okay, and I have to use sudo whenever I need to use Docker because it needs admin privileges to run. So for the rest of this lecture, I'm going to switch the user to be root in order to avoid having to prefix my commands with sudo. Okay, and as you can see here, sudo docker images is a command that shows you the images that are installed on your machine. And because we have used docker run in a previous lecture of this section to run the hello world container or to run the hello world image, we have this image stored on our machine. Just the same as Vagrant boxes, if the image has been downloaded on your machine, it won't be downloaded again once you start using it. It's gonna be used to launch as many containers as you need without having to download the image again. Once it's downloaded, it stays on your system. So let's clear the screen, and I am going to use sudo su dash in order to change my user account to be root, in order not to have to type sudo, just to save time and typing. So using Docker followed by a subcommand is how you interact with Docker, and Docker actually offers the --help, which is a very valuable switch because it's going to give you help on the subcommand that you are using. If you are curious how to use a subcommand, what are its different switches and options, and you want to have a general idea about its usage, just type the subcommand followed by --help, like docker images --help, and as you can see here, it will give you all the options of this subcommand. Okay, so in order to run a Docker image, you have two options: either to run docker run, just like that, and docker run will automatically fetch the image for you if it does not already exist on your system, or maybe you want to download an image and you want to use it later. So let's say, for example, you want to use an image that is called BusyBox, and BusyBox is a Linux kernel, a tiny Linux kernel that has the basic functionality. It is not a fully blown OS, just has the most basic Linux functions. So it is often used with the when you want to have an example that runs a Linux kernel just for the basic Linux usage. So I can use docker pull and give it the name of the image. Our image is called BusyBox. Docker pull will only pull the image on your local system, and it will be cached on your system. It won't be re-downloaded when you want to use it to run a container. So docker pull BusyBox is going to search for this image locally first, and if it is not found, it is going to be downloaded from the repository. So as you can see here, it is very tiny image, just 700 kilobytes as you have just seen. And now I can spawn containers out of this image. So to spawn a container or to launch a container, use docker run. And docker run is often used with a switch like, for example, --detach, which means that this server or this container is going to be run in the background. So why would you want to run a container in the background, or how a container is actually run in the background? As we have just mentioned in the first lecture of this section, containers are nothing but abstracted applications. Think of a container as an application, just an application. An application can be run in the foreground, or it can be run in the background as a service or as a daemon. So Docker deals with containers just like you deal with processes or with applications. You can run the container in the background the same way you run an application in the background. So --detach will ensure that the application is run on the background, and you can regain control of the shell to type other commands. Then --name, and it's a good idea to give a name to your container. --name server will give the container the name of the server. However, if you did not assign a name to the container, Docker will assign a name for you and an ID. Have a look here at this long series of characters and numbers. This is called the image ID, and a similar ID is created for the container, which is used as a unique identifier for the container on the system. So now we can identify the container both by name and by ID. We're gonna see that in a moment. So the last parameter we need to add to docker run is the name of the image on which this container is based. In our case, it's BusyBox. And since we do have BusyBox already installed on our system or deployed on our system, it won't be downloaded. So if I press return, it is going to create the container just like that without having to download the image again. So this container is running now in the background. If you want to make sure that it is running, run docker ps. Of course, you are familiar with the ps command used on Linux to list the currently running processes. Docker ps is a similar command, but it's gonna display the running containers. And as you can see here, I don't have anything running. That is because in order for BusyBox to run, it has to have a command to run. It has to have something that will keep it running in the background or in the foreground. So let's clear the screen, and in order to make this container continue running, you will have to use a command that will keep it running, because as we have just mentioned, Docker containers are nothing but applications, nothing but processes. For a process to keep running, there has to be some sort of a loop or a command that keeps it running in the background. So let's run the same command again, docker run --detach, or I can also add -d, which will give me the same functionality. It will run the container in the background. So docker run -d -name server. It will also be based on BusyBox, and this time I'm going to issue this command: while true, do sleep 5. Done. this is just an infinite loop. It does nothing but sleep every 5 seconds and then sleep again for 5 seconds and so on and so forth. So it does nothing. However, it is sufficient to keep a process running, and because a process is running, the container will not stop. The container will not exit. It will keep running in the background because there is a process that is running indefinitely. So if I press enter now, you're gonna see that we have a problem, we have a conflict. That is because I already used the name server with a container that has been created in the system. Although this container is stopped, it is actually being identified in the system with a name and an ID. So you cannot use the same name for a different container. You have two options now, either to remove this container or to create a new container with a different name. So in order to remove the container, I'm gonna use docker rm and give it the name of the container. And rm is short for remove. It is very similar to the rm command that is used in Linux to remove files and directories. So docker rm server. Now I can run the same command again. Of course, it's gonna give me a different ID. And now if I run docker ps, you're gonna see that I have a container ID. This is the shortened version of this long string of characters and numbers. And this is the image. This is the command that keeps the image running. And this is how long it's been created. And this is the name of the container, and these are the ports that it has exposed. So what if you want to stop the container manually? Just issue docker stop server. Okay, it's gonna take a few moments. Okay, it has been stopped. If you want to start it, you're gonna issue docker start server. Okay, and it is started again. You can also do docker restart server, and it is going to restart the container. So what if you want to connect to this container? What if you want to connect to it via command line and, like for example, list the files that are there or examine the machine itself or the underlying operating system? So let's stop and remove the container, and now I can use a slightly different command. I'm gonna remove the sh-c, which created the infinite loop, and I will add -i and t to the container. -i is short for interactive, and -t is short for tty. Interactive means that you want to interact with this container, which means that you can access it via the shell and issue commands directly to the container. And -t or -tty or -tty means that this container accepts the process signals. If you worked with Linux for some time, you would know that processes accept signals from the shell, like the kill signal, for example. So if you want this container to act as a process, a normal Linux process, you will have to add the -t. It is recommended to use this combination of switches, and we're going to use them whenever we are running a Docker container throughout this section. Now, if I press enter and ensure that the process is running, although I don't have a command or an infinite loop that keeps the container running in the background, I do have this container running. And that is because I use the -i option. The -i option means that I need a shell in this container. And this shell, as you can see here, the command is sh for the Bourne shell. Now, if I want to access this container, I will use docker attach server. Docker attach and the container name. If I press enter, I am inside the machine. Actually, I'm not inside Ubuntu anymore. I'm inside the machine. As you can see here, these are the file systems on my machine. This is where I'm standing. I'm standing at /. Okay, and as you can see here, the cursor or the prompt has changed to be a hash, meaning that I am logged in as root. But observe what happens if I exit this shell. Now, if I run docker ps, I'm gonna see that I do not have any containers anymore. That is because I have exited from the shell. When I did exit from the shell itself as a process has exited. It has finished. When you exit from the shell, this shell is no longer running. And when the shell is no longer running, which is the only command that keeps the container running, the container itself is stopped. So I guess this gives you a better idea about what containers is, how you can connect to them, how you can start them, how you can stop them, how you can remove them, and how you can access a container that is running an operating system using the shell, just like you connect to it using an SSH command. And that brings us to the end of this lecture. In the coming lecture, we are going to start by discussing how Docker networking works, how to connect to a network service that is running on your Docker container. So until then, see you next.